Have you ever wondered if time could stop? What if we told you it does, in a black hole? In the vast expanse of our universe, black holes are one of the most enigmatic phenomena. They're regions of space where gravity is so strong that nothing, not even light, can escape their grasp. These cosmic monsters are so dense that they warp the fabric of space and time itself. But what happens to time in these extreme conditions? To understand this, we delve into the realm of Albert Einstein's theory of relativity. This theory, which revolutionized our understanding of the universe, suggests that time is not constant. Time dilation might sound complicated, but let's break it down. Imagine you're watching your favorite action movie, and suddenly the scene goes into slow motion. The protagonist is leaping through the air, every detail of the scene unfolding slowly. The seconds on your watch are ticking away at their usual pace, but in the world of the movie, time has slowed down. This, in a nutshell, is time dilation. Time moving at different rates in different places. Now let's bring black holes into the picture. These celestial phenomena are known for their immense gravitational pull, so powerful that not even light can escape. But what does this have to do with time? Well, according to Einstein's theory of relativity, gravity is not just a force pulling things together, it's also a warping of space and time. The stronger the gravitational pull, the more warped the space-time, and the slower time appears to move. This is where time dilation comes into play in a black hole. As you get closer to a black hole, its gravitational pull becomes stronger and stronger. This intense gravity warps space and time around it, causing time to slow down. From a distance, the closer you get to the black hole, the slower time appears to move. Now let's take this one step further. If you were to fall into a black hole, to an observer watching from a safe distance, time for you would appear to slow down. As you get closer and closer to the event horizon, the point of no return, your movements would appear to slow to a crawl, and eventually, you would seem to freeze in time. So, if you were to fall into a black hole, from an outside observer's perspective, you would appear to slow down and eventually freeze in time. This brings us to a paradox, doesn't it? If time stops in a black hole, how can anything ever fall in? Let's take a moment to grapple with this conundrum. It seems like a contradiction, right? On one hand, we have this notion of time grinding to a halt as we approach a black hole. Yet simultaneously we know that objects, and even light itself, can be sucked into these cosmic vacuum cleaners, disappearing forever. To reconcile this paradox, we need to venture into the realm of relativity and the way it impacts our perception of time. So imagine you're observing a spaceship, let's call it the starlight, as it approaches a black hole. From your perspective, far from the black hole's influence, you'd see the starlight's clock ticking slower and slower as it nears the event horizon, the point of no return. It would appear as if time on the starlight is coming to a standstill. Now here's the twist. From the perspective of the astronauts aboard the starlight, time wouldn't seem to be slowing down at all. Their clocks would tick away at a normal pace, their perception of time remaining unaltered. They wouldn't feel time slowing down, even as they crossed the event horizon and plunged into the black hole. This disparity arises from what's known as time dilation, a key aspect of Einstein's theory of relativity. When you're observing from a distance, you're seeing the effect of the black hole's immense gravity on the light signals coming from the starlight. The closer the spaceship gets to the black hole, the harder it is for these signals to escape, which makes it seem as if time is slowing down. In other words, while it may seem like time stops in a black hole, it only does so from an outside observer's perspective. It's all about where you're standing, or rather, floating in the vast expanse of space. The universe, it seems, is not just stranger than we imagine, but stranger than we can imagine. So, what have we learned about black holes and time? We've delved into the enigmatic nature of black holes, celestial bodies so dense and powerful that not even light can escape their gravitational pull. We've learned that these cosmic giants can bend space and time, leading us into the realm of time dilation. In our journey, we've simplified the concept of time dilation, understanding that the stronger the gravitational field, the slower time appears to pass. This phenomenon is not just a figment of science fiction, but a reality confirmed by our understanding of Einstein's theory of relativity. We've also unraveled the paradox of time seemingly stopping in a black hole. While it's true that to an outside observer time appears to stand still at the event horizon for someone falling into a black hole, time would seem to pass normally. Time might not literally stop in a black hole, but its effects certainly make it seem like it does, and that's just one of the many mysteries that black holes hold.
Don't forget to like, subscribe and share this video. That's all for Nifty Narration.